Y'all ready for math? All right, here we are, folks. Mr. Berto back again. Here's our second lesson on differential equations. So really, I think the ditto was like 1.1 or something like that. This is 1.1 continued. We're going to continue with solving differential equations today. We'll do your homework problem first. So you should have tried number 4 for homework. Okay, you could have done number 5 as well. We did the solution last video. Let's just go through this. I don't know if you could follow my chicken scratch or not, but why not review a little bit before we get to a different type of problem today. Also, you might notice over here, you can see my granola bars and a peanut butter jar. It's my emergency supplies here, and this is what I have to work with. Okay, so I wish I had a nice little video setup, but it is the way it is. Stop laughing at me. So number 4 here, consider this differential equation. Let y equals f of x be the particular solution. So that's y equals form once again, and they're going to want you to find that. They give you a little initial-condition action, right? And they want you to find the particular solution of the differential equation that passes through the point -1, 2. Okay, the same thing as the initial condition over there. Sometimes they'll write it in point form. Sometimes they'll kind of write it in function form over here. And they want you to find y equals f of x. And normally that's the way it's going to be. Remember, a differential equation is an equation with a derivative in it. How do we go from a derivative to an original? We integrate. But first, y'all got to separate, and that means to cross multiply. That's the first part of it anyway. dy times 2 is going to be 2 dy. Remember, Mr. Berto's tips and tricks, always keep the dy on the left-hand side equal to -x y squared dx. And remember, Mr. Berto's tip and trick number 2, make sure you keep the left-hand side as clean as possible. So this 2, he doesn't need to be there, okay? What needs to be there is the y squared, not the negative, not the x, just the y squared. So I'm going to divide by y squared on both sides. At the same time, I'm going to divide by 2 on both sides, okay? Leaving this 2 over here can cause so many issues, you have no idea, okay? So instead of dividing by 2, only Sabrina would divide by 2. I'll multiply by 1/2 on both sides, and I'll also multiply by 1 over y squared on both sides. So that'll give me 1 over y squared dy is equal to -1/2 x dx. Hopefully you realize how I got there. If you don't, pause the video, think about it. Okay, all I do is really divide by 2 on both sides, divide by y squared on both sides. Before you integrate this puppy over here, because we do have variables that are separated, I'll make this y to the -2 dy. Makes it a bit easier. Ava can do that better. Equals -1/2 x dx. And let's integrate, y'all. Integrate. Don't differentiate. Get it straight. Oh, man, I'm losing my mind. Okay, so here, let's add 1 to the exponent. -2 plus 1 is going to be -1. Divide by that number. Mr. Berto's tip and trick number 3. Don't put the plus c on the left-hand side, okay? It's always going to be moved over to the right anyway. Here's my -1/2 times the integral of x to the first, which we know is x squared over 2. Make sure you put the plus c on the right-hand side, okay? And now, I don't know, divide by -1, same as multiplying by -1. So negative y to the -1 equals what? -1/4 x squared plus c. That's a general solution right there. Okay, and remember, I never solve for y until I solve for c first. That's another tip and trick. But you can eliminate constants on both sides. You could divide by -1 on both sides or multiply by -1 on both sides. Whichever way you want to write it out, we know there's no difference there. All right, and that's going to give me y to the -1 is equal to, and I'm multiplying by -1 over here. Sorry about that, folks, okay? -1 times -1/4 x squared is going to be +1/4 x squared. And then -1 times c, remember, just another c, okay? So, and right here, you could use this if you want to as your general solution. I'll make the y to the -1 1 over y. And if you make 1/4 x squared into x squared over 4 plus c, it makes things a little bit easier. Right now you got to be careful. People are like, I want to solve for y. Well, think about it. If you solve for y, you'd have to, take the reciprocal of both sides. That's an advanced algebraic technique. I don't perform any advanced algebraic technique unless I know what c is equal to. Okay, be very careful with that because it can cause issues. I'm going to stop right here. Before you do anything crazy, solve for c. It'll make things easier. I know y is going to be +2. So 1 over 2 is equal to, we know x is -1, so -1 quantity squared over 4 plus c. And here we end up with 1/2 is equal to 1/4 plus c. So you subtract 1/4 from both sides. 1/2 minus 1/4 is just going to be 1/4. So I get 1/4 is equal to c. All right, now I'm going to make sure that I plug that into this general solution. So 1 over y is now going to equal x squared over 4 plus 1 over 4. And you can see why I wrote it as x squared over 4. Now you can see we got those common denominators. Okay, so here we could actually get 1 over y equals x squared plus 1, quantity over 4. And now it's easy to take the reciprocal of both sides. So you can only take the reciprocal of both sides when you have one single fraction on either side. Okay, over here, you don't have one single fraction on either side. People want to say y is equal to 4 over x squared plus c, because they're like, oh, the reciprocal of a constant is just another constant. Yeah, you can do that, okay, but you can't do that if there's two separate fractions connected by addition. Here's the answer we're looking for. You know, if you wanted to go that route, you'd have to say this is 1 over y is equal to x squared over 4 plus c over 1. And you need to get common denominator of 4 right here, right? Multiply by 4 top and bottom. Because if you want to just take the reciprocal of both sides before you solve for c, you got to get a single fraction on either side. So here I have 1 over y is equal to, this is x squared over 4 plus what? 4c over 4. You could even say 4c right there is just another c, so you could call that c. So basically you get 1 over y is equal to x squared plus c over 4. Then take the reciprocal of both sides. And then you could actually get your, value of c. And it's going to be different. We can see right here, if you want the same particular solution, our c here has to equal to 1. People are like, oh, c equaled 1/4 though. But that was the c that went with this general solution. The c equal to 1 is going to be the c that goes with this general solution over here, okay? This general solution. Okay, so if you actually want to plug in -1 comma 2, so y is 2, x is going to be -1. Okay, that's going to give us 2 is equal to 4 over what? 1 plus c. Cross multiply here. Already this is annoying. Okay, 2 times the quantity, 1 plus c equals 4. Divide by 2 on both sides. 1 plus c equals 2. And we can see we actually get c equal to 1. Okay, so if you want to use this version right here, make sure you plug this c into it. I guess it'll be somewhere over here. Okay, and we're going to get 4 over x squared plus 1. So we get the same particular solution. So different general solutions can generate the same particular solution. They might have different values of c. I don't suggest going here. I really don't. Okay, it makes it so much easier if you just solve for c before you do any advanced algebraic technique like reciprocating both sides. Anyway, that's all I have to say about that. You know, so if you actually take a ditto from yesterday, here's our ditto from yesterday, right? Remember the menorah over here. Okay, if you actually turn the sheet around, turn it round and round, where my backing vocals out there, you'll find this problem right here, which Martina said often the equation will involve a logarithm, which used to be the most popular type of problem on the AP exam. There's all kinds of differential equations now, but it seems harmless at first. We get dy over dx equals 3x squared y, and they give us nice little nishkin dish. They want us to find an equation for y in terms of x. Okay, so we need that particular solution. Hey, cross multiply, put the dy on the left-hand side. dy times 1 is dy equal to 3x squared y dx. If you think you're separated, you're tripped out of your gourd, okay, because you can see that this y needs to be over here. Don't be bringing the 3 over here, putting a 1/3 over there. You could do it, but it's going to cause, disaster. Maybe not. But the x squared, definitely don't be bringing him over there. So I'll divide by y on both sides. Same thing as multiplying by 1 over y on both sides. And some people actually take this y, they bring it upstairs, make it y to the -1, but you actually don't want to do that, okay? Because we know how to integrate 1 over y, just like the integral of 1 over x is ln absolute value x. The integral of 1 over y is ln absolute value y. Technically plus c, but we're going to put that c on the other side, right? Integrate 3x squared, that's somebody's derivative in there. Whose derivative? X cubed's derivative. Okay, and here's where I'm going to leave it for my general solution, because if you want to solve for y right now, you'd have to make both sides an argument of e, right? An exponent of e, and that's e, an advanced algebraic technique. And I don't perform an advanced algebraic technique until I solve for c. So you can see these problems, situations where if you want to integrate a quotient, the bottom's not being raised to a power. Don't be bringing that bottom upstairs, raising it to a negative power. It's really an ln situation. You could do the ln trick, right? Take the derivative of the bottom, derivative of y with respect to y is 1. We can see that derivative is up top. So it's ln absolute value of the denominator usually plus c, only we already moved the plus c over there. Now I know my niche condition, right? Y of 0 is 2, so the point 0, comma 2 lies on said function. All right, so when y is equal to 2, we get ln absolute value 2 equal to x is 0. The absolute value of 2 is 2, so we get that the ln of 2 is equal to c. All right, let's make sure we actually use this general solution, which is the one we used to generate this particular value of c. Plug back in there, ln absolute value y equals x cubed plus ln 2. Now we're not dealing with that c. It's going to make things a little bit easier. But now you want to make both sides an argument of e, right? An exponent of e, because e and ln cancel each other out. So now you're left with absolute value of y is equal to e to the quantity x cubed plus ln 2. You know, this absolute value thing can cause some snarky situations. Remember, the absolute value of y, there are two ways to take the absolute value of a number, okay? If that number happens to be positive, you just take the absolute value by dropping the absolute value signs. And that's a situation where if y is positive or equal to 0, it does make a difference for absolute value. But if y happens to be a negative number, you're going to want to negate it. So if y is negative, less than 0, you're going to want to negate it to take the absolute value. So sometimes absolute value y is y, and sometimes absolute value of y is equal to negative y. Well, in this case, y is equal to 2. Okay, and that's what you want to do. You want to look at your particular solution, just like you had to do for the square root yesterday. You know, here I see that y is a positive number, so the absolute value of y is just going to be equal to y, okay? You know, the absolute value of 2 is just 2. That's why in this case, we're going to say y is equal to e to the quantity x cubed plus ln 2, which, by the way, is not a bad particular solution, okay? It's not incorrect. Every now and then in multiple choice, you'll see it looking like this, but what they'll do in these cases is they'll say, oh, addition of exponents means that like bases must have been multiplied. And look how cool that is, right? If you multiply like bases, you add exponents, so you'd end up back here. But now we know e to the ln 2 is just equal to 2, and you could actually put that 2 in front. We end up with y is equal to 2 e to the x cubed. And that's the way they'll have it written in multiple choice. Part 2, you don't have to worry about this. You could leave it here, but get used to this, okay? Remember, I know that you're like, well, our AP exam is only free response, you know, coronavirus. You know, your life is going to go on, okay? You guys are going to be in college. You're going to need to know how to do these types of things, okay? So it's important we still speak about everything, okay? So if you actually end up having to integrate a quotient and the bottom's not being raised to a visible power, well, then it's an ln type of situation. And the thing that gets snarky is that absolute value and also turning addition of exponents into multiplication of like bases. Let's see what this would look like, you know, on an AP exam, not Mr. Martinez's handwriting. 2004, okay, right there is a year I like to forget as far as the World Series. Pretty sure there wasn't even a World Series that was played in 2004. Yankee fans understand what I'm talking about. We want to consider this differential equation. Find the particular solution y equals f of x to the given differential equation with the initial condition f of 0 equals 3, which means what? The point 0, comma 3 is going to be on the original function. And look, let's get into it. Let's separate and then integrate. Remember, cross multiply, Mr. Berto's tips and tricks, an online strategy for solving differential equations. Okay, dy times 1, put the dy on the left. dy equal to, we get x squared times the quantity y minus 1 dx. We are not separated. You know, we want to move this y to the left-hand side. Remember, that's not a y. That's a y minus 1, okay? That minus 1 is chained to him right there. So I got to divide by the entire quantity y minus 1 on both sides. Same thing as multiplying by 1 over the quantity y minus 1 with respect to y equals x squared dx. Okay, so now the variables are actually separated. You got to keep them separated. Bow, 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 bow. I don't know if you know that song. Anyway, so my variables are separated. Now let's integrate, get it straight, don't differentiate. Okay, and here, you know, a little wonky. Don't be making this y minus 1 quantity to the negative 1. This is an ln, okay? If you want to integrate a quotient, the bottom's not being raised to a visible power, try to take the derivative of the bottom. And we know the derivative of the bottom here is equal to 1, right? The derivative of y minus 1 with respect to y is going to be equal to 1. And that derivative is up top, perfectly matched. That means the answer is ln, absolute value of the denominator, no plus c, because we're going to put it on this side, equals x cubed over 3 plus c. Okay, so now, you know, think about it. The next step, like if there was a 2 over here, You could multiply by a half on both sides or divide by 2 on both sides. You could wipe out constants from the left-hand side. But whenever you have to use any type of advanced algebraic technique to solve for C, to solve, for Y, pardon me, well, that's going to be an issue if you don't know what C is equal to. So if you're smart, you'll stop right here, be like, the next thing I need to do is make both sides the argument of E. That's an advanced algebraic technique. I don't solve for Y until I solve for C. We know 0, 3 is our initial condition. Okay, so if Y is equal to 3, ln absolute value of the quantity, 3 minus 1, that's going to become important later, equals 0 cubed over 3 plus C. So you actually get ln of absolute value 2, which is just ln 2 equal to C. So the same C from the last problem. That means it's a shoddily engineered lesson. Just kidding. Okay, that can happen, all right? And now I'm actually going to plug into that general solution I used to generate this value of C, ln absolute value of the quantity y minus 1 equal to x cubed over 3 plus ln 2. Now, when you make both sides an argument of E, it makes it a little bit easier to see what's going on. You know, people write the E down here. I did it in the previous problem. Technically, this is what's going on. I'll rewrite. You don't need to necessarily rewrite here, but why not? Why not? Y sub 0, why not? Here the E and the ln cancel, but be careful because now we have absolute value of the quantity y minus 1, a little bit different from the last problem. It was just absolute value of y, equal to, I'll do this on the right-hand side though, make it e to the x cubed over 3 times e to the ln 2. Right, addition of exponents means like bases have been multiplied. And now this y minus 1, you need to consider whether it's positive or whether it's negative. Okay, remember y is equal to 3 here. So if y equals 3, that means y minus 1 really equals 3 minus 1, which equals 2. That's positive, okay? So it's not always just about what y is equal to when you're taking the absolute value. It's whatever's in the absolute value. See, if this was a y minus 2 and y was equal to 1, 1 minus 2 would be a negative answer. And if you get a negative inside an absolute value, you got to negate what's in there. You'd have to make this negative y plus 1. We're going to see a problem like that soon enough. Who knows, one might show up on your homework. But right now, if y is equal to 2, y is equal to 3, 3 minus 1 is equal to 2, 2 is a positive number. To take the absolute value of a positive number, you could just drop the absolute value sign. But if you got a negative number in here when you plugged in that initial condition, you would have to make this negative y plus 1. You'd have to negate the whole thing. This over here is equal to, 2 e to the x cubed over 3. Okay, add 1 to both sides. Y is equal to 2 e to the x cubed over 3 plus 1. And that's going to be our particular solution that we're looking for, okay? And these problems can be crunchy, okay? Differential equations, they don't seem too terrible, but when you get into it, they can get rough, okay? Try to follow my tips and tricks. Number 1, put the dy on the left-hand side. Number 2, keep the left-hand side as clean as possible. What am I pointing at? Something you can't even see. We didn't have to do anything to clean up the left-hand side here, but if there was like a 3 or a negative over there, we'd move it back over to the right. When you integrate, tip and trick number 3, make sure you put the plus c on the right-hand side. And then remember, I don't solve for y until I solve for what c is equal to. If there are constants on the left-hand side, I will move them over. Okay, so always keep the left-hand side as clean as possible. That's tip and trick number 2. But make sure you solve for c before you solve for y, and that'll just make it easier for you to end up with the correct particular solution. There are a lot of different ways particular solutions can look. Okay, this is what they're looking for on the AP exam, but you could have something that's equivalent on a free response and you'll still get the credit for it. Okay, we'll talk tomorrow in the next lesson about what these differential equations represent. Like I said, it's really a family of, in this case, a strange type of exponential function here, okay? And depending on what the value, well, this is actually a particular solution, so that's just one, strange type of function. But depending over here on what the value of c is, you could generate infinitely many functions, okay? And tomorrow we'll talk about something known as the slope field, which is really a representation for this general solution using little pieces of tangent lines, okay, that we could generate using the differential equation. Anyway, that's something we'll speak about tomorrow, so do the best you can with these problems. Email me or send me a, remind, let me know how I'm doing. If you're struggling on stuff, just do the best that you can, okay? Believe it or not, you're in a much better situation than you might think, okay? So once again, everybody stay home and healthy. Hope everybody's family is doing well, and we'll see you all next time. It's Berto signing out. Adios.